This is Lesson 7 in our Calculus 2 series, Inverse Trigonometric Functions. Recall from Lesson 1 that the only functions to have inverse functions are the one-to-one functions. Now, trig functions are not one-to-one on their entire domains, but we can restrict the domains and talk about inverse functions. So let's take a look at f of x equals sine x. If we're going to restrict the domain here, we're looking for a set of x values for which the function achieves all of its y values. And we notice that if we look at the set of x values from negative pi over 2 to pi over 2, including both endpoints, y equals sine x achieves all of its y values over that interval. So that's a good choice for our restriction of the domain. Now, you might think, well, why can't we choose pi over 2 to 3 pi over 2? Well, you can, but that's just not the same inverse function that we're going to talk about here. So when we restrict the domain to negative pi over 2 to pi over 2, f of x equals sine x is then one-to-one, and we can talk about its inverse function. We're going to call that inverse function arc sine of x, or sine inverse of x. Then for the original function, y equals sine x, the domain is negative pi over 2 to pi over 2, and the range is negative 1 to 1. And so for the inverse function, y equals arc sine x, the domain is going to be negative 1 to 1, and the range is going to be negative pi over 2 to pi over 2. Remember that when you're talking about inverse functions, since the roles of x and y are switched, the domains and ranges are switched as well. So just to be clear about this inverse function, when we say y equals arc sine x, that's the same as saying x is equal to sine of y. For example, sine of pi over 2 we know is equal to 1, and pi over 2 is in the restricted domain. Therefore, pi over 2 is equal to arc sine of 1. Similarly, sine of negative pi over 4 is equal to negative radical 2 over 2, and negative pi over 4 is also in the restricted domain of negative pi over 2 to pi over 2. So that says arc sine of negative radical 2 over 2 is equal to negative pi over 4. Let's evaluate arc sine of 1/2. Now we know that what comes out of the arc sine function is an angle. So let's call that theta. And what do we know about theta? We know that sine of theta must equal 1/2, and theta must be in the interval negative pi over 2 to pi over 2, because that is the range of the arc sine function. So we think about our sine values, and we realize that sine of pi over 6 is equal to 1/2, and pi over 6 is in this interval. So arc sine of 1/2 is equal to pi over 6. Now notice that 1/2 is a sign evaluation for one of our common first quadrant angles. What happens if we had something like negative 1/2 here? The answer wouldn't be pi over 6. So let's see what happens when we need to do a little bit more work. Let's take a look at arc sine of negative radical 3 over 2. Again, we know that this must be an angle value, so we're going to call it theta. Now, what do we know to be true about theta? We know that sine of theta must equal negative radical 3 over 2, and theta must be in the range of arc sine x, which is negative pi over 2 to pi over 2. Now, when we go and look at our table, we know that sine of pi over 3 is positive radical 3 over 2. So the answer here is not going to be pi over 3, but we're going to use pi over 3 to help us find the answer. We're going to use pi over 3 as our reference angle. So what we want to do from here is draw the angles in all four quadrants that have reference angle pi over 3. So that's pi over 3, 2 pi over 3, this would be 3 pi over 3, so this is 4 pi over 3, and 5 pi over 3. So now we have the angles in all four quadrants that have reference angle pi over 3. Now, which of these angles has a negative sine value? Well, the sine function is negative in quadrants 3 and 4. Quadrants 3 and 4. Also, we know that theta must be in the interval negative pi over 2 to pi over 2. That is represented by quadrants 1 and 4. So we know that theta must be in quadrants 1 or 4. Now, we know that theta must have both of these properties, so it must be that theta is in quadrant 4. And the angle that we're looking for is here. Now notice when I drew the angles in each quadrant, I called this one 5 pi over 3. But 5 pi over 3 is not between negative pi over 2 and pi over 2. So actually we have to call this angle negative pi over 3 in order for it to be the proper solution here. Remember that 5 pi over 3 and negative pi over 3 are coterminal. So theta equals negative pi over 3 is our solution. Now before we go on to the arc cosine function, I just want to remind you of the composition of inverse functions. We have that arc sine of x is equal to x for the x values in the proper domain here. So for x values in the interval negative pi over 2 to pi over 2. When we compose in the other direction, we have sine of arc sine of x, and that's equal to x as well. And that's for x values in the domain of arc sine. So that's for x values in the interval negative 1 to 1. And that's by composition of inverse functions. Now let's take a look at f of x equals cosine x. Again, we're looking for an interval of x values over which the cosine function achieves all of its y values. So we're going to take the interval from 0 to pi. We can see that on that interval, the cosine function achieves all of its y values and each only once. So we restrict the domain for y equals cosine x to be from 0 to pi, and then its range is going to be from negative 1 to 1. We call its inverse function arc cosine of x, or cosine inverse of x. And its domain is going to be negative 1 to 1. Its range is 0 to pi. And just as we had with the arc sine function, saying y equals arc cosine of x is the same as saying x equals cosine of y. So let's take a look at a couple of examples. We know that cosine of pi over 2 is equal to 0, right? That's on our graph here. Cosine of pi over 2 is equal to 0. And we also know that pi over 2 is within this domain, 0 to pi. Therefore, we can say pi over 2 is equal to arc cosine of 0. Similarly, cosine of 0 is equal to 1, and 0 is within the interval 0 to pi. So we can say that 0 is equal to arc cosine of 1. Now let's evaluate arc cosine of negative radical 3 over 2. Just as we did in the previous problems, we're going to call this theta. And what do we know? We know that cosine of theta must equal negative radical 3 over 2, and theta must be in the interval 0 to pi, because that is the range of arc cosine x. Now we know that cosine of pi over 6 is radical 3 over 2, so pi over 6 is our reference angle. So we're going to draw the pi over 6 angles in each quadrant. This one is pi over 6. This one is 5 pi over 6. 7 pi over 6. And 11 pi over 6. Now we know that we need cosine theta to be negative. And we have all students take calculus. So where is cosine negative? That happens in quadrants 2 and 3. We also know that theta must be in the interval 0 to pi. That's quadrants 1 and 2. So our solution then must be in quadrant 2. And so theta equals 5 pi over 6. For tan x, if we have f of x equals tan x, our inverse function we call arctan x, or tan inverse of x. So saying y equals arctan x is the same as saying x equals tan y. And again, we're looking for an interval on x in which the tan function now takes on all of its y values and each only once. And so we choose the interval from negative pi over 2 to pi over 2. But notice that the endpoints cannot be included here because the tangent function is not defined at x equals negative pi over 2 or at x equals pi over 2. So we've got the open interval here as our restricted domain on the tan function, and so that's going to be the range of the arctan function. And notice here that the range for the tangent function is all reals, so the domain for arctan x is going to be all reals. So for example, we know that tangent of pi over 4 is equal to 1. That's here. And we know that pi over 4 is within the interval from negative pi over 2 to pi over 2. Therefore, we can say pi over 4 is equal to arctan of 1. Now, the arctan function often comes up in limit evaluations. So let's take a look at what's happening here. For y equals tan x, that's the graph that we're looking at here, we can see that as x goes to pi over 2 from the left, as x goes to pi over 2 from the left, the y values are going towards infinity. And that's happening for y equals tan x. So, for y equals arctan x, now we're switching the roles of x and y here. This is the inverse function. Then, if x is going to infinity, y must be going to pi over 2 from the left. So here's the graph of y equals arctan x. What we're saying is as x goes towards infinity, the y values here are going towards pi over 2 from the left, from values that are smaller than pi over 2. And so we can write limit as x goes to infinity, arctan of x is equal to pi over 2. And so then let's take a look at limit as x goes to negative infinity, arctan of e to the negative x. What's happening here? As x goes towards negative infinity, negative x goes towards positive infinity. Now, what's happening to the graph of e to the x when its exponent goes towards infinity? Here's the graph of y equals e to the x. As x goes towards infinity, that value goes towards infinity as well. So this is going towards infinity. So now we're looking at the limit as x goes towards infinity of arctan x, and that is pi over 2. Now the other inverse trig functions are defined similarly. I'm not going to go into details here about any of these. One thing I want to point out though is that in each of the functions we talked about already, the restricted domains that we used are universal. That'll show up in every textbook. But for cosecant x and for secant x, you'll see different restricted domains depending on the textbook that you use. Now let's talk about derivatives and integrals with inverse trig functions. To find the derivative of arcsine x, we're going to use the relationship between the derivatives of inverse functions. So we learned that in lesson 1. We have g prime is equal to 1 over f prime of g of x, where f and g are inverse functions. So if we let f of x be sine x and g of x be arcsine x, then we know f prime is cosine x, and g prime is then 1 over cosine of arcsine x. That's f prime of g of x. Now we need to simplify this. So let's take a look at how we can do that. We need to simplify cosine of arcsine x. Just as we were doing before, let's call arcsine x theta. And what do we know about theta? We know that sine of theta is equal to x. Sine of theta is equal to x. We can write that as x over 1 and set up a right triangle. where sine of theta is represented as opposite over hypotenuse on the triangle. So here's our angle theta, and we know that sine of theta is x over 1. So the opposite side has length x, the hypotenuse has length 1. And then with the Pythagorean theorem, we can find the remaining side. Because what do we need? We need cosine of theta. Cosine of theta is going to be adjacent over hypotenuse, so that's radical 1 minus x squared over 1, or just radical 1 minus x squared. So this simplifies to 1 over radical 1 minus x squared. And so the derivative of arc sine x is 1 over radical 1 minus x squared. You could also find the same result using implicit differentiation. If we let y equals arc sine x, that's the same as saying x equals sine y. Now let's differentiate this equation both sides with respect to x. On the left, we get 1, and on the right, we get cosine y dy dx. So we solve for dy dx, and that's 1 over cosine y, and now we need to be able to write this in terms of x. So just as we did above, we look here and we have sine of y is equal to x, so that says sine of angle y is equal to x over 1. Sine of angle y is equal to x over 1. By the Pythagorean theorem, we find that the remaining side is radical 1 minus x squared. And so cosine of y is adjacent over hypotenuse, and that's radical 1 minus x squared. And so that goes in our denominator here, and we get the same answer. So we have the derivative of arc sine x is 1 over radical 1 minus x squared. That says the antiderivative of 1 over radical 1 minus x squared is going to be arc sine x plus a constant. Notice this is the first integration rule that allows us to solve something like this, because if we tried a u sub on this integral, we would have u equals 1 minus x squared, and du would be negative 2x dx. And we're missing a factor of x here. So this is very useful for us for integration. Now one thing I want to point out, arc sine of x only exists for x values from negative 1 to 1. And 1 over radical 1 minus x squared only exists for x values between negative 1 and 1. So I just want to point out that in order for this integration rule to hold, there can't be any x values for which this exists, for which this does not exist. And there aren't, so that's fine. Now let's take a look at the derivative of arctan x. I'd like you to use the methods above to find this derivative. So please pause the video and work on that. For f of x equals tan x, the inverse function g of x is equal to arctan x. We know that f prime of x is equal to secant square x, so g prime is equal to 1 over f prime of g of x. That's 1 over secant squared of arctan x. And now we need to simplify this. So, similar to what we did above, we let theta equal arctan x, and then we know that tan theta is equal to x, or x over 1. Tan theta is opposite over adjacent, so we set up our triangle, and the side opposite angle theta has length x, the side adjacent to angle theta has length 1, and by the Pythagorean theorem, we find that the hypotenuse has length radical 1 plus x squared. Now we're looking for secant square of arctan x, so that's secant square of theta. So that's hypotenuse over adjacent quantity squared. So that's radical 1 plus x squared over 1 quantity squared, or 1 plus x squared. So going back up here, we have 1 over 1 plus x squared. And so the derivative of arctan x is 1 over 1 plus x squared. And so that says the antiderivative of 1 over 1 plus x squared is equal to arctan x plus a constant. And again, this is very useful for us in integration. So here are all of the inverse trig derivatives. We talked about 2 of them above. but here are all of them. And notice that the derivative of arc cosine x is just negative of the derivative of arc sine x. That's true with tangent and cotangent and secant and cosecant. So when it comes to integration, if we have the integral of, say, negative 1 over radical 1 minus x squared, we could write it as negative arc sine x plus a constant. That's perfectly fine. So let's take a look at an example. Here we want to find the derivative of arctan of 1 over x. So we're going to have to use the chain rule here. Now we know the derivative of arctan x is 1 over 1 plus x squared. So the derivative of arctan of g of x is going to be 1 over 1 plus g of x quantity square multiplied by g prime of x. So here f prime is going to be 1 over 1 plus 1 over x quantity squared multiplied by the derivative of 1 over x. So that's 1 over 1 plus 1 over x squared. We can simplify here. And then the derivative of x to the negative 1 is negative x to the negative 2, so that's here. Now just to simplify, we can write this x squared in the denominator and multiply through. And so we're going to get negative 1 over x squared plus 1. And so we found the derivative we're looking for. We were asked to find f prime of x, and we found that. But notice, this is the derivative of arc cotan x. So let's explore this a little bit. We found that arctan of 1 over x has the same derivative as arc cotan of x. So are those functions the same? Or maybe do they differ by a constant? Let's take a look. Let's call arctan of 1 over x theta. That says tangent of theta is equal to 1 over x. Tan of theta is equal to 1 over x. Now if we take the reciprocal of both sides here, we get cotan of theta is equal to x over 1. Cotan of theta is equal to x over 1. Okay, and this says that theta equals arc cotan of x. So yes, this is true for all x, of course not equal to 0. Now let's take a look at an integral. We have 1 over radical 1 minus 16x squared. Now I look at this and the first thing I notice is a composition, and I might want to think about trying u equals 1 minus 16x squared. But then I notice my du is going to be negative 32x dx, and I don't have a copy of x here, so that's not going to work. But then I remember my inverse trig derivatives, and I recognize that this is similar to the derivative of arc sine x. This 16x squared here is actually 4x quantity squared. And so we want to recognize this composition and do a u substitution with u equals 4x. And then in that case, du is equal to 4 dx. So we need a 4 in our integral. And so we put a 1/4 on the outside. Now switching over to u's, we need to change our bounds. When x is equal to 0, u is also equal to 0. So that goes here. And then when x is equal to 1/8, u is equal to 4/8 or 1/2. So that goes here. Now we want to take our antiderivative. And so we have 1/4 arc sine of u going from 0 to 1/2. So that's 1/4 of arc sine of 1/2 minus arc sine of 0. Remember that arc sine of 1/2 is the theta value for which sine theta equals 1/2, and that theta must be in the interval negative pi over 2 to pi over 2. So that theta is equal to pi over 6. And arc sine of 0 is the angle for which the sine value equals 0, also in the interval from negative pi over 2 to pi over 2. And so that angle is 0. So we've got 1/4 times pi over 6 minus 0, so that is pi over 24. and that's the value of this definite integral. And with this, we'll conclude our lesson on the inverse trig functions.